Welcome to The Explainer. I'm your host, The Strategist, and today we are tackling something I like to call the weightlifter strategy. I want you to picture a competitive weightlifter for a second. They do not expend their energy flailing around the gym, right? They don't do random unstructured movements. They apply absolute maximum effort in short, highly concentrated bursts. We're talking explosive power. And honestly, that is exactly the mentality you need for high-mark questions in computer science. Today, we're diving incredibly deep into exactly what separates a solid B from a flawless A-star in Cambridge computer science and information technology. We're specifically focusing on syllabus 9626, section 4.2, editing given flowcharts and identifying errors in algorithms. But listen to me closely. Whether you are sitting for syllabus 0417, 0478, 2210, 9618, or 9626, the strategy we are unpacking today is the absolute universal blueprint for your success. To really set the stage here, I want you to mentally transport yourself into the exam hall right now. Ticking clock, absolute silence, high stakes. Picture two students sitting there. Let's call them Alex and Sam. They're staring at the exact same Cambridge past paper question. It's a complex flowchart trace table problem. Now, Alex is sweating. Alex is aggressively writing down every single fact about flowcharts they can possibly pull from memory. They are completely overloading the page with raw computer science facts, but there is absolutely zero analysis, just a massive data dump. Sam, on the other hand, is rushing. Sam is frantically looking at the clock, completely skimming over the specific command words, and just trying to sprint to the finish line. When the examiner's red pen comes out, both Alex and Sam lose massive points. Why? Because they lacked the explosive, targeted strategy required for high-mark questions. They had the knowledge, but they lacked the execution.
So, you have to ask yourself, what actually separates a B from an A-star in identifying flowchart errors? The answer fundamentally comes down to moving past rote memorization and delivering the context-specific, highly analytical responses that examiners are actually hunting for. Let's look at Alex's paper for a second. Alex wrote a giant half-page paragraph defining exactly what a loop is and how a while loop differs from a for loop. The examiner gives that entire paragraph 0 marks. 0. Because the question didn't ask for a textbook definition. It asked why the specific loop in the provided flowchart failed to terminate. Now look at Sam's paper. Sam actually identified the error. They spotted an off-by-1 error in a counter. Brilliant, right? But Sam completely missed the command word explain. So they just stated, the counter is wrong, and moved straight on. Red marks everywhere. You leave so many points on the table when you do this. To bridge that massive gap between a B and an A-star, you can't rely on luck. You need a system.
Here is our highly structured playbook for today, designed to systematically upgrade your exam responses from superficial to top tier. 1. The A-star difference. 2. The procedural framework. 3. Top 3 examiner warnings. And 4. Critical analysis and evaluation.
Okay, let's jump straight into section 1, the A-star difference, where we talk about why depth will always beat breadth. The difference between Alex's B-grade answer and an A-star answer is entirely about depth. The Cambridge assessment frameworks target distinct cognitive domains. Basic knowledge and understanding are just your baseline. They get you in the door. But application and analysis, that is where the real points are won, especially in 9618 and 9626. You have to decode the command words. Does the prompt say state, describe, explain, or evaluate? Because each one of those requires a totally different level of explosive power. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, back to the strategy. Examiners aren't looking for a list of random facts. They prioritize systematic analysis. Notice Alex's superficial breadth. Alex wrote, a flowchart uses diamonds for decisions and rectangles for processes. Great. True, but completely generic. Compare that to the analytical depth we really want. The decision symbol at step 4 causes an infinite loop because the counter X is never incremented within the iterative process. To reach that top-tier answer, top students use the Peel framework. Point, evidence, explanation, link. Your point. The error is an infinite loop. Your evidence. Look at step 4 and the variable x. Your explanation. The counter is missing an incrementation step like x equals x plus 1. Your link. Therefore, the termination condition x greater than 10 is never met. If you forced yourself to apply the Peel framework to your algorithm questions, you physically cannot write a superficial answer. It's a built-in safety net.
Let's transition into section 2, the procedural framework. This is where we talk about earning those absolutely critical method marks.
In computer science, the examiner is very rarely just looking for the final right answer. If you are fixing a broken algorithm or editing a complex flowchart, there are points awarded purely for your methodology. If you skip steps, even if your final answer is somewhat correct, you leave marks on the table.
When you are tackling examination questions on flowcharts, you need to follow this exact 5-step procedural framework to guarantee you hit the assessment objectives. Step 1. Deconstruct the question. What exactly is the scenario? Is it an automated payroll system, a temperature sensor array in a greenhouse? Circle the command word immediately. Step 2. Extract data. Pull the variables, the constants, and the initial states out of the flowchart. If there's a trace table required, set it up now. Step 3. Select your analytical framework. Are you going to dry run the code line by line? Are you scanning specifically for syntax errors or logical errors? Step 4. Execute with clear notation. When you write out the corrected algorithm, use proper, standardized conventions. Step 5. Present with correct terminology. Please, never say the box that asks a question. You have to say the conditional statement or the selection construct. Professional terminology is non-negotiable. To make absolutely sure you do not forget this when you are under severe exam pressure, I want you to use the DESEP mnemonic to lock in these critical steps. Deconstruct, extract, select, execute, present. DESEP. Think back to our weightlifter. This mnemonic is your stance. You would never walk up to a 300-pound barbell, grab it, and just violently yank it off the floor without checking your grip, checking your footing, and taking a deep breath. DESEP is how you set your mental stance before you lift a heavy 12-mark flowchart question. Imagine Sam from earlier. Sam is rushing through the exam. Because they are panicking about time, Sam completely skips the extract step. Sam doesn't write down the initial value of the variables before starting the dry run. Because of that one skipped step, Sam traces the entire flowchart incorrectly and identifies the completely wrong error. If Sam had just taken a breath and used DESEP, they would have realized the variable was initialized at 1 instead of 0, which completely changes the loop iteration count and the entire outcome of the trace table.
And remember, your presentation of information during the execution and presentation steps must rigorously follow strict technical conventions. We are talking about proper headings in your trace tables. Column 1 is your loop counter I, column 2 is your array index, column 3 is the running total. It needs to be pristine. We're talking about correct terminology. You must know the difference between an assignment, a declaration, and an output. We need appropriate formats, meaning if you're asked to redraw a section of a flowchart, you use a ruler. You draw crystal clear directional arrows. You ensure your text inside the shapes is perfectly legible. Clear annotation means adding brief, targeted comments to your code or diagram to explain exactly why you made the change you did. Let's visualize a transformation right now. Think about Alex and Sam. They're sitting there rewriting their answers live using this blueprint. Alex realizes they need to stop data dumping and start targeting. The red pen marks are literally transforming into green check marks. Why? Because instead of writing a massive block of text about what a Boolean data type is, Alex has drawn a beautiful, perfectly formatted trace table with proper column headings for every single variable, clearly showing the exact row where the algorithm's logic fails. That's explosive power.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, we're moving to Section 3, Top 3 Examiner Warnings. This is all about avoiding the biggest pitfalls.
Every single year, Cambridge publishes examiner reports. And let me tell you, these reports are absolute gold mines. They tell us exactly where thousands of students, just like Alex and Sam, crashed and burned. According to the actual principal examiners, these are the top 3 traps you absolutely must avoid when identifying errors in algorithms. Number 1, confusing cause and effect. Number 2, forgetting format and presentation. Number 3, answers lacking specific context. We are going to do an interactive workshop right now. Challenge 1, the data scan. I am mentally putting a 60-second visual countdown timer on the screen for you. Ready? Imagine a complex flowchart mapping a smart home heating system. The prompt states, the heater never turns off. The temperature just keeps rising. Students constantly confuse cause and effect here. They will write down, the error is that the heater stays on. No, that is the effect. The cause is the decision box logic reading temperature less than 20 instead of temperature greater than 20. You have 60 seconds in an exam to extract that core trend. You have to look for the root cause deep in the algorithm, not just point out the symptom. Now for challenge 2, find the flaw. The timer is back on. I'm going to give you a flawed sample paragraph based on trap number 3, lacking context. Listen closely. The algorithm is wrong because the loop doesn't stop. To fix it, you need to add an input inside the loop so the user can change the data. Okay, time's up. Can you spot exactly why that answer loses almost all its marks? The examiner commentary would absolutely tear that apart because it lacks specific context. Which loop?
There might be 3 nested loops. What input? Which specific variable needs to be changed by the user? It's way too vague. You aren't proving to the examiner that you understand the specific system in front of you.
Let's look at how a top student builds context. Generic answers lose marks instantly, while top-tier answers anchor every single observation to the specific data provided in the prompt. This brings us to challenge 3, speed writing. I want you to imagine a 30-second timer counting down right now. It's ticking. Your task is to mentally write one perfect Peel paragraph, point, evidence, explanation, link, for a flowchart that fails to calculate an average because the total is divided by a hard-coded number 10 instead of the variable count. Ready? Go. Your point. The average calculation logic is incorrect. Your evidence. In the final process box, the formula is average equals total divided by 10. Your explanation. The denominator is a hard-coded constant of 10, but the flowchart actually allows a variable number of inputs, which is tracked by the count variable. Your link. Therefore, to fix the logical error, the expression must be edited to average equals total divided by count to ensure dynamic accuracy no matter how many times the loop runs. Boom. Time's up. That is exactly how you get maximum marks in minimum time. That is the Peel framework in action.
Finally, let's explore Section 4, Critical Analysis and Evaluation. This is how you elevate your response to lock in that A-star grade. What's really crucial on this slide is the definition of comparative analysis. When you get to the higher levels like 9618 or 9626, it's not just about spotting a missing directional arrow in a diagram. It's about evaluating the efficiency, the robustness, and the fundamental logic of the given solution. Top-scoring candidates constantly question assumptions. You must master comparative analysis by not just spotting differences, but systematically evaluating both similarities and differences, and backing it up with direct evidence from the code. Sometimes an exam will give you 2 completely different flowcharts that solve the exact same problem, like 2 different array sorting algorithms, and ask you to evaluate them. Alex would just look at them and say, Flowchart A is shorter. Sam might say flowchart B uses a while loop, but flowchart A uses a repeat loop. Both of those answers are going to get minimal marks. An A-star student uses comparative connectives. They write, whereas flowchart A utilizes a post-condition repeat loop, ensuring the code executes at least once, regardless of input, flowchart B employs a preconditioned while loop, which is significantly more robust in this scenario because it prevents execution entirely if the initial sensor data is invalid. Do you see the difference there? You are supporting the comparison with hard evidence and drawing a highly specific conclusion about its relative importance to the scenario.
Your overall problem-solving approach should always follow this deconstruct, solve, evaluate loop to ensure every single recommendation you make is fully justified. This is your complete computer science answering system. Follow this and your marks will soar. Step 1. Identify given information. Step 2. Break the algorithm down into logical steps. Step 3. Solve it systematically using a trace table. Step 4. Check for reasonableness. This is massive. If your trace table outputs a negative age for a person or a temperature of 1,000,000 degrees for a living room, it is not reasonable. Catch your own errors before the examiner does. Step 5. Justify your recommendations. This ties directly into our 3 golden rules that guarantee top marks: command word decoding, Peel framework application, and your time management matrix. Do not spend 15 minutes agonizing over a 3-mark syntax question. Allocate your explosive energy where the points are heaviest.
I want to leave you with this absolute golden rule directly from the examiners themselves. Listen to this alert. Always link every point to the given scenario. This is the ultimate cheat sheet recap. If the question is about a self-driving car's obstacle detection algorithm, your answer better mention proximity sensors, braking speeds, and physical obstacles, not just generic variable X and variable Y. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
So ask yourself this question before you walk into your next exam. Are your answers just generic memorization, or are they evidence-based, Peel-structured evaluations of the specific scenario? Are you an Alex, a Sam, or are you the strategist who lifts heavy and lifts smart? Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.